From Benard Peuto and several other people who are involved with the Computer Museum, the Computer Museum's History Project. This is a new branch of the Computer Museum, and like the computer industry itself, it's suffering from exponential growth. Without any further ado, this is Benard Peuto, now a consultant, but with a long history of historical computers.
Yes,
and I'll let you explain that, Benard.
I guess that's why I lost all my hairs. Basically, I am not going to attempt to cover 50 years of history in 1 hour, but I'm going to try to get close to it. And I'm specifically going to talk about mainframe concepts that were developed during the mainframe era and that has been imported into the microprocessors. And in order to achieve this goal, I'm going to basically talk about a very quick timeline about mainframe, some of the early challenges that mainframe had specifically with technology. Then I'm going to show that a very similar set of timeline existed for microprocessor. And then I'm going to go into each of the points that I expect to spend most of my time on, which deals with specific things and challenges that were in the microprocessor era, where we can see that they copied the concept from the mainframe era. In trying to finish, I will show you in my mind, most of the interesting concept dealing with virtual memory, application focus, and some issues about a new application focus that might exist for microprocessor. Then I'll give you a conclusion, and if we have time, I'll flash a small bibliography about it. If we look at mainframe and we try to simplify the history quite tremendously, we can say that there are essentially 6 periods of roughly 10 years that separate the beginning of the mainframe era to today stopping in this case in 1994. There's a pioneering period from 37 to 46, then the first computers, 45, followed by broad product, meaning product really being used by everybody, followed by what I consider to be the zenith of mainframe era, and we'll talk more about why I think so, competition for microprocessors, and restructuring. When people talk about mainframe pioneers, this is the period where essentially computers were invented. There are 4 products that are generally mentioned but do not fully qualify as being the invention of the computer, which is widely regarded to be the ENIAC. In 1937 to 39, George Stibitz at Bell Lab did a mechanical relay calculator that was computing and being able to do some computational operation. Atanasov and Berry developed a prototype of a computer in 1937 to 42, but it was never fully built, and thus it never executed a program being able to give result of computation. Historically, there have been a set of battles about who invented the computer, and we'll discuss more about that later. And in some sense, legally, Atanasov is the inventor of the computer, but his computer never executed an algorithm. Hyken at Harvard with IBM designed a computer from 1937 to 44. So it took them 7 years to build a very large relay computer. This computer is very famous because it gave the name of Harvard architecture to an architecture in which you have the data memory and the program memory being in different medium. And then there is always a motion, which is quite deserved, of Konrad Zuse, who in Germany in 1941 built the Z3, a relay computer, and this was not known for quite some years because of the war. The war had another effect on computers. Is one of the most interesting computer that I believe was an early computer was the Colossus computer. It was a secret computer until the 1970s because it was used in England to do code breaking. It was essentially invented by Alan Turing and built by Flowers and Newman. There was in 1941 a relay version, and in 1943 a tube version. Very little is mentioned in books about this, except for the fact it might not have been dedicated to code breaking. I think it is very close to being the owner of the title of first computer. But in fact, we all agree today that the ENIAC is the first computer that was built. It was digit-based, 10-based, not binary. It had a panel-like devices in which you would enter information and programs. And it was using tubes, and it was electronic, and it was executing approximately 5,000 operations per second. It took 3 years to build it, and its original target was to do table building for shells being shot by the government at the time during the war. And it was essentially doing computational tables for artillery shells. There's several other noteworthy computers like the Manchester Mark I. I have here with me a picture of the ENIAC. I don't know what is the best way to do it this way. It was very large physically. It had more than 10,000 tubes. I said it executed approximately 5,000 operations per second. And there was a lot of very smart feat of engineering in the usage of tube, which at the time was not obvious to people. It was not obvious to people that you could build a computer due to the reliability of tube. It might have never worked since there was 10,000 of them, so one of them would be always dead at any one point in time. This is the kind of equation that the computer physically solved at the time. This is dealing with, sending a sharp object in space. Let's call it a gun shell or something of that nature. It worked for many, many years. I mean, I think it was around 4 to 6 years. I do not exactly know, doing this work, which is the reason why I consider it to be basically the first computer. Now, going to my next list of computers, it happens that after the invention, after the pioneering work, we now deal with a period of time where computers are being built, in fact, for commercial applications. And the starting of this pioneering period is 1945, when John von Neumann, Ecker and Mauchly are the two inventors of the ENIAC, wrote a document which was basically authored by John von Neumann but got ideas from many people, that talked about what we now call stored program computer. As you remember, the ENIAC was not a stored program computer, and that was the principle of the EDVAC. It happens the EDVAC was built very slowly because Eckert and Mauchly left the Moore School of Engineering in a disagreement with management on patent rights. And so the first computer that implemented the stored program architecture and essentially started the era of mainframe was the EDSAC in England, influenced by the EDVAC paper and built by Maurice Wilks. You will find out that Maurice Wilks is one of the extraordinary pioneers in this business because he has invented a tremendous amount of things in computers. The first commercial computer to be shipped was again in England. It was the Ferranti Mark I, which was shipped in early '51, not the Univac, which is generally well known to be that, which was shipped in later '51. But in essence, it's also interesting to know that the first commercial computer user was General Electric. This is a picture of the EDSAC. And now we are entering the era where computers are basically being commercially sold. One of the first early computers being commercially sold again is the Leo computer in England. And then IBM gets into the business. IBM was the dominant vendor at the time of data processing equipment based on card processing. In case you don't know what a card is, this is a card. Okay? And what happened is the business, IBM started with a 701 in 1953, which was a scientific computer. At the time, the differences between scientific computers and commercial computers already occurred. And one was character-based, the other one was computational-based. The 650 is a very important computer that was introduced at that time because it was the first computer that had a drum memory. We will talk more about that, but at the time, memory was often in delay line or William tubes, which were essentially CRT tubes used for memory. And the 650 had a drum memory. That meant, all the memory was on the drum. The program was on the drum. The data was on the drum. There was no other memory in the computer. Whirlwind is a very important computer. It was a project at MIT in 1949 that dealt with the first real-time computer. And it was built by a professor named J. Forrester, and he's the inventor of core memory. This is a picture of J. Forrester holding, in fact, a core memory. I will show you an identical device to this one. And this is what the Whirlwind computer looked like. Notice there was a fire extinguisher at the end. The Whirlwind computer was used in the SAGE development. SAGE was the airborne defense program that was used to protect us from missiles coming from nasty nations. Because he invented the core memory, this is a page from his notebook that shows you the date and the concept of a core memory and two wires going through it. In reality, An Wang may be the person that thought about the core memory, and Forrester is the person that thought about the addressing. The combination of the two created a core memory, and since we're talking so much about core memory, I'm going to show you one. This is a core memory from Whirlwind. It is a 1000-bit. Massive improvement over, by the way, what it was to use a Mercury dealer line, which was as big as this table, like a supercharged washing machine, and use propagation of sounds on Mercury to hold the bits. So this was dramatically more reliable and dense. Yeah. Okay, now I had also a chart about the 650. This is the console of the 650. At the time, people considered the computer as their companion for the night, I guess, and everything was often used with a front panel which you would sometime enter the program in. Remember Altair, same thing. And that you would also view some result from. And you will see this is a 650 console. I will show you other pictures of console that are much larger. As computer grew, so did the console. Now we are going out of this period. We have covered the following period. We have covered a pioneering period here. We're now getting into first computers, okay? And we are now getting into broad products. And broad products is when computers really become commercial. And then we will have major product lines, computation, and restructuring. So those are the major phases that I talk about. And I'm going to talk about a computer that created an whole industry by itself, the RAMAC. The RAMAC was the first computer. Now, RAMAC, I believe, stands for Random Access, I can't remember even that. Random Access, something about accounting, method of accounting computer, something like that. And it was the first computer that had a disk drive. I'll show it to you. This is the RAMAC, and you can see in the background the disk drive. Now, IBM invented the disk drive and was a pioneer in having most of the disk drive development taking place. Now, this is another picture of the disk drive itself. You can see it. I believe the diameter of those disks was 54 inch. There was at least 20 or 30 of those, and it stored 5,000 characters. A character was probably 6-bit at the time. So this was a 3.5 megabyte disk, being big as a washing machine on super steroid. 1,200 rotation per minute, and that was considered to be such a high speed that it was creating very significant mechanical problem with the drive. So, tells you a little about that. Now, the IBM became a dominant vendor really as soon as the 650. Univac was the company that had the first product. Univac was the company that had probably the best product at first. And they had also bad management. And there is a very famous line by a computer pioneer called Grosch that says, and I sometimes miss the line, that says that Univac had the talent to snatch defeat out of the jaws of victory. And basically, IBM, because of its superior management, essentially destroyed them. By 1962, as an example, Univac had their third machine, and most of those machines had been incompatible, and essentially at that time IBM was dominating the world. One of the very important machines to talk about also this period is the 1401. You remember IBM was a company that had been the dominant vendor of accounting system based on card. The 1401 in 1960 is the first machine that was more economical to use than a card system. The dominant vendor of card system was obsoleting its own product line, a story that IBM will repeat several times. So this is a manual of a 1401, and at the time, 1960, people were obviously conveniently sexist, so you would always see a woman next to the computer, in this case to the printer, the 1403 printer, card reader, and the computer itself. There's another picture where she's conveniently putting a tape drive. The 1401 was in fact used by IBM to dominate the commercial side of the business. This is an assembly line for the 1401. Now, assembly line for computers are something that would not seem too classy, but this is the way they were building them, essentially by hand in very large warehouses, and you can see the Tektronix scopes in the front. Okay. This period of broad product has to be finished by 2 or 3 major products that I want to mention because they had very significant influence on the industry. The first one, and I'll talk much more about it later, is the Atlas, an English machine in 1962 that was the first machine to have pagination, page virtual memory. The Honeywell 200 is the first clone machine. It was a clone on the 1401. So the notion of cloning a computer to take advantage of the software developed by its vendor was a notion that was introduced in 1964, and we know it's a notion that has been popular ever since. The next 2 computers were a response to a request by the government. The government asked in 1959 to build an advanced computer that would be 10 times faster or bigger than the technology of the time. And that computer would have been called, or that program would have been called the Livermore Advanced Research Computer. The people that got the contract was UNIVAC, and they built a computer called the Lark. IBM was so frustrated about it that they continued the development of their own computer, which was responding to that proposal, called Stretch, 1961. Stretch is, in my mind, one of the most important computers ever built because it represents the most striking advances, and it happens most of the technology of Stretch was used by the 360, which we're going to talk about in a minute. This is the console of Stretch. So you can see that progress in technology means bigger consoles. Okay. This is an image that was very common in mainframe. Mainframe were this, large rooms with raised floor and air conditioning in which you would have the devices being laid off by the vendor, and they would often have those kinds of drawing. So this is a Stretch, okay, and what it looked like. And this is a photograph of the Livermore Stretch. It happens the Computer Museum History Center owns the complete Livermore Stretch that was used at Lawrence Livermore Lab. And I remind you, there was only 8 Stretch ever built. Now we get into the next period, which is the period where already IBM owned 70% of the market, but they managed to be even more stunning by announcing a new product line called the 360. The 360 was a product line of 8 to 10 computers from 360 model 30 to 360 model 91, and they were all having the same instruction set, the same types of peripheral. They were using microprogramming in order to implement, depending on different technology, the same instruction set. That instruction set is one of the most and best designed instruction set that I think has ever been done. It is still used today in the IBM computers called the 390 in a binary compatible fashion with that instruction set. There have been some significant changes in the I/O architecture, but not very much changes in the instruction set architecture. 2 very critical computers of the 360 are the Model 91, which we will talk more about later, which represent essentially the invention of pipelining. This is the computer that invented most concepts about pipelining. And the 360 Model 85 because it invented the concept of cache memory. Cache memory has been invented before, but this was the first major product that used it. Okay, now I have a picture for you of a 360. I believe this is probably a Model 50. Okay, and you can see this other disk drive with disk drive that were removable type disk drive. And this is printers and card readers and tape drives that you see in the back. This is a picture of a 360 Model 85. I have to tell you that this kind of honeycomb design was fairly frequent at the time because people were trying to have the memory being as close to the CPU physically as you could. And although I do not know that for a fact, it could very well be one of those bays, the cache. I mean, memories was pretty bulky at the time, and the technology used was pretty bulky. So we now have IBM having introduced the 360 in 1965, revolutionized the industry, and what happened is the seventh dwarf, there was IBM and the seventh dwarf fall by the wayside. Basically, RCA&G abandoned the computer business in 1970, and so the seven dwarfs, which were, I can never remember all their names, RCA&G, Honeywell, NCR, Control Data, became the branch. The branch is easier to remember. The branch is Burroughs, Univac, RCA, NCR, and Honeywell and CDC. So anyway, basically, IBM is at the peak of their power. Whenever they sneeze, the whole industry catch a cold. And at that point, basically, a newspaper talks about IBM. Nowadays, newspapers talk about Intel. At that time, it was newspapers talk about IBM. I do not cover at all, because I don't have the time, mini computers or workstation in this talk. But I couldn't help showing you another interesting pictures from the 70s. This is the PDP-11. And again, sexism seems to be going to miniskirt at this point. The reason we get into a zenith of IBM is somewhat fairly complicated, but I'll spend a few minutes talking about that. IBM introduced the 370. The 370 was the next generation using transistor for memory of the 360 architecture. And they introduced that machine in 1970, and the first shipment is in 71. In August 1972, they announced to the world that all those 370 that had been shipped could now execute virtual memory, which had been introduced, you remember, with the Atlas in 62. And IBM also had a machine called the 360 Model 67 that implemented virtual memory. But essentially, IBM was telling the world, virtual memory is not for scientists, meaning MIT, Multics. Virtual memory is for running your bank account. And so everybody rushed to having virtual memory at that point. And so the 370 Model 68 was the first one to be shipped in 1973. So I look at August 1972, and I look at this announcement, and the whole industry essentially, Amdahl had to redesign their computer. The whole industry essentially slaved to IBM's announcement, despite the fact IBM had not invented virtual memory, but the fact they made it commercial made it popular. And I look at that same year, or roughly 1971, the microprocessors being introduced. Nobody would have thought microprocessors were going to influence mainframe, but we're going to talk more about that. In reality, they did. And so this is the peak of their period. They will have some very good years, but they will not control the business anymore the way they used to. As a matter of fact, in 1975, in the era of competition, when the era started, you would never think that IBM didn't control the world. At that point, Amdahl Corporation introduced a product called the 470 V6 in 1975. Amdahl was ready to introduce a product called the 470/5, I think. I was there, I remember that. And they basically stopped shipping their product, changed their architecture, because IBM had announced virtual memory. John Koch at IBM in research invented the RISC architecture with the 801. IBM introduced a very advanced disk of 512 megabytes called the 3370. IBM, which had for years a limitation in their actual implementation of software, in their architecture, you could have addresses that were 32-bit, but only 24-bit were used in the 360. The 8 upper bit were used for sundry type application in the operating system. They got rid of those 8 upper bit, increasing the architecture power to 31-bit addressing. That was the 370 model XA. I mean, you think IBM would rule the world, because who would care, like I, to leave Amdahl Corporation to go to Zilog? Who would think that microprocessors were going to amount to anything? But in my opinion, by 1985, when the 386 was shipping, people had realized that microprocessors were going to change the world of mainframe. And so in those 10 years, basically, we switched the emphasis from being mainframe-centric when it came to computer to being microprocessor-centric when it came to computers. This is a picture of the Amdahl chips. You can see those are fins that would, on which air would blow. The Amdahl computer was one of the first high-end computer that was air-cooled. At that time, computers were cooled using water, piping. Then comes the sad period of the mainframe that I call restructuring. During that period, IBM does introduce the 390, but it is also a period in which there is the first layoff at IBM. There is a shrinking differentiation between the CPU of a 390 and a Pentium Pro are basically the same kind of power today. So the distinction between mainframe and microprocessor becomes an issue of legacy application, RAID, disk farms, communication across long distances, and those kinds of issues, which are significant business, but which are not in the focus of everybody. Like I said, Intel, Microsoft, and the web dominates. So now I have finished my rather brief history of mainframe. I'm going to talk for the next few minutes about the subjects of technology, the technological challenge that mainframe had, which microprocessor never faced. And then we'll go into our microprocessor portion. Basically, the challenge that they faced were reliable memory. Like I've already alluded to, there were for many years rather unreliable memory being used. They did have to decide what an advanced ALU was. That means inventing floating points and inventing instruction set architectures. And then they did have to design reliable peripheral. Some of those points I'm going to cover later in the talk, and so I'll skip them for today, for now. In case you don't know, punch cards were invented in 1804 for looms. They became again important. This is a punch card. They became important again around 1870 when Hollerith invented a card reader. And in the 20s and 40s, punch cards were essentially used to do business accounting and other kinds of business processing. And you should not underestimate the computational power of punch card machine when the computer came out. Meaning, in 1951, you had not tube-oriented, but semi-electronic, relay-oriented machine that could essentially add, subtract, accumulate, make decisions, punch new output, which would become the new data for some further process. As we talked about, relay were used, but I'm going to focus on tube for the next few minutes. And in the case of tube, I just want to mention to you, in case you don't know, that the tube was invented in 1906. It was significantly used in radio and telephony during most of those years. And the ENIAC was a tube computer. It was quite a significant decision to decide that you could use tube for computers at the time the ENIAC decision was made. The 1709 was the first tube computer by IBM, the last tube computer by IBM, and around 1960s were the last tube computers ever used. I have here for you a 704 tube module. You can see the tubes here, and you can see, I'll lose it that way, you can see the resistors and other elements that were used. There's a diode here, capacitors, and so on. This was the kind of size that you had in the computers of that time. We'll talk more about some of those issues as we go. Okay. Now I'm going to talk about what happened to memory. Basically, we've already discussed it. Memory started with pure flip-flops. That was the arithmetical units of the ENIAC. Mercury Diller line as big as this table. Williams tubes, which is using the side of the tube to have spot of charge, which then later would be read to find out the value. Great advantage was the speed of the Williams tube. Then magnetic drums, we talked about it. And then core memory, I already showed you core memory. Semiconductor memory took until 1970 for IBM to use it, but I believe RCA had semiconductor memory in 1965. And you should all know that Intel started as a semiconductor memory maker. When it comes to magnetics, I think we've covered already most of those points, so I will skip the slides. And then I will want to talk about the evolution of transistors and packaging. This is really the theme I want to talk about now. And this will complete the issues of technologies and mainframe. Notice all of those technological issues end up around 1970, which is the time where microprocessor gets started, meaning that between roughly 1970 and 75, all major technological issues of mainframe hadn't been solved. That meant that microprocessor could benefit for all those developments when they introduced personal computers based on microprocessors. I've always fascinated to know that printed circuits were invented during World War II, and that basically the early 50s is the first commercial printed circuit. Integrated circuit was invented in 59. IBM had a technology called SLT. This is SLT technology, okay, which is a set of, let me try this way. This is SLT technology, which is a set of active components on a substrate. This was the closest to being an integrated circuit MSI style as you could get. And this is how IBM would use it as an example. They would use it in blocks like this. So this was a card. So this is 1965 technology that I'm showing to you. I'm going to show you technology that was before 1965. This is DEC equipment, a card doing some minor function. I suspect it may be written on the back. It doesn't say. Which use transistors and printed circuit card. This is the same kind, obviously a lot more of it, now using ICs. Okay? And what you have to realize is the development of packaging technology as well as the development of computer were some of the most important impact on the ability for people to have more powerful computers. The same way today's packaging technology impact in having denser line on silicon is the dominant factor to making it happen and increasing the power of microprocessors. Now, having done all those comments about mainframe, I hope I can delve into the issues of microprocessor. And what I want to show to you again is the slide that I've shown you before, which is this is the time frame for mainframe. You don't have to read all of it, just get the sense of it. This is 50 years in 10 years increment. This is a time frame for microprocessor. This is 25 years in 5 years increment. And trust me, most of the phases are essentially the same. So one of the first comments you can make about microprocessor is we did in 25 years what it took them to do in 50 years. And why did we do that? It's because basically we copied most of what had been invented before. So the microprocessor era started in 1971 with the introduction of the 4004, and this is the first phase. There's no pioneering phase. We don't have to invent computers. They've been invented before. And in that phase, there is quite a development. It's very rapid. For example, in 1972 is the 8008, and in fact the 8080 is 1974, but it genuinely belonged to the next era. This is a picture taken in November of this year of the four inventors of the 4001, Federico Fujin, Ted Hoff, Stan Mazer, and Masatoshi Shima, and in the background here you see the 4004. And this is the first device that ever had a microprocessor in it. This is a prototype of the Busicom calculator. Busicom was a Japanese company which contracted Intel to build, in essence, what became the 4004. And this prototype was the one that was owned by Federico Fujin. It is one of the artifacts of the museum. And he used it a lot of the time to compute, size of transistors and so on. So not only is this prototype the first device ever built that had a microprocessor in it, but we could also say this is the first CAD machine that had a microprocessor in it. And this is a copy of the inside of it, and you can see the gold packages are some of the chips, so the 4004. There were several chips that made, it was a multi-chip family in reality. And to the best of my knowledge, it would work today, but we've never dared to try. Okay. Now let's go back to my slides. After the first microprocessor, we see a tremendous amount of activities and lots of vendors try to get into the business. One of the most noteworthy of those vendors is obviously TI, which in 1972 did a product called the 1795, which supposedly worked, which they never shipped. Talk about missing an opportunity. And basically, we see Motorola getting into the game in the next phase, what I call broad product. Broad product is we now understand what microprocessor is. We're starting to talk about software, development system, tools, peripheral chips. So we're talking about things that are very much closer to a mini computer, in fact, or to a personal computer later. And this is the era exemplified by the 8080, the 6800, and the Z80 at Zilog. I was at Zilog when the Z80 was being designed. And then we get into the next era. But before we get into the next era, we must talk about one of the major developments that took place in this business. Originally, a lot of the people thought that microprocessor might be logic replacement, meaning taking a card like this and replacing it with a microprocessor and memory and making it have different functionality. So there was some kind of a battle between people about, are microprocessor a data processing systems or are they hardware replacement logic? The second kind of battle that took place was the concept of, are we going to be data processing oriented, or are we going to be like the 8048 or the Z8 which were product introduced again in this time frame, which were single chip microcontroller, which are used in essentially inside of a product without you really being able to program it. So this battle took place, and by the way, it will be resolved in some later years. But to fuel the battle were personal computer based on microprocessor. The first one, is a French product that was done in 1973 and based on the 8008. So the first personal computer based on a microprocessor was built in 1973 based on the 8008. And what's his name? Oh, I can't remember. What? T-Cron. And the programmer on that machine was Philippe Kahn. Okay. The most famous personal computer based on a microprocessor is the Altair, which was introduced in 1975, and this was based on the 8080. Okay. And there was a lot of other personal computer build that were based on the Z80, like the TRS-80, that was around 1977, or based on the 6502, which was a variant of the 6800, and there was the Commodore PET and the Apple 1 and 2. So in fact, there was a tremendous amount of activity in that period that dealt with establishing, in fact, a beachhead for microprocessors to be the dominant element of a personal computer and thus of personal data processing. IBM did introduce in 1981, after the 16-bit were introduced, the 16-bit are 78, the 8086, and the Z8000 and the 68000. The 8088 was introduced in 79 and was the central element of the IBM PC, itself introduced in 1981. IBM used a very clever advertisement technique of using Charlie Chaplin lookalike and telling you that this was going to help you in your life and this was going to be very easy for you to use. I still ask myself that question, but okay. Then we get into the next phase. And by the way, I'm trying to go somewhat quickly in those phases because in a minute I'm going to talk about the technical feature itself, where we really enter in a phase of competition. That's from 1985 to 1989. The competition, by the way, is Intel is crushing the competition. That's what the competition is all about. And all of the vendors, like the Zylogs and the National, and only survivors, Motorola in this case, all the vendors that had introduced 16-bit product and were introducing 32-bit product, essentially by 1989, were out of the game because microprocessors had been identified as being the core element of the personal computer, and personal computer meant Wintel and x86 compatibility. So what happened is Zilog has a product called the Z80,000, National had a product called the 32016. Both of those products had advances that Intel would have several years later, but that doesn't matter. They were not used in personal computers, and thus they faded away. Let me now get into the issues about what we essentially copied from mainframe. So let's go back to 1971 and say this is the date, this is the year where Federico Fugin and several other people designed the 4004, and why did they design that architecture? And what was the available knowledge at the time concerning microprocessor? Well, Stanford had built its computer science department in 1961. Most computer science departments under federal government help had been built in that period. So there was at least 10 years of computer science education that was available to anybody that knew computer in 1971. The products that were important were the 317, the PDB-11, that were used as model in teaching, and the operating system that was important was Multics, Unix, and a little OS 370, depending what you talk to. And basically, with very few exceptions, this was not used at first by microprocessor designers, and the reason are pretty simple, is most of them were, in fact, silicon gate designers that understood enough about computers to copy some of it, but not fully to do the right kind of architecture. And so what we see is that it's around 1976 that people like myself with computer science degree get hired by the Intel and the Zilog and the Motorola, and then it's a few years later, by 1979, with a 16-bit microprocessor, that people with architectural background gets to design microprocessors. Now, by the time 1985 of the 386, that would not have been any question. Everybody designing microprocessor had a computer science background. So the early challenge at first is copying the PDP-8. Ted Hoff will tell you that he attempted to copy the PDP-8 in designing the architecture of the 4004. And that period takes roughly from 71 to 84, to, excuse me, 71 to 74, when the 8080 appears. The 8080 is not the best architecture one could like, but at least it was reasonably clean and there was no major forgotten feature about it. Then they go into a period which is quite different, which is responding to the request by their customer to sell them, in essence, a mini computer on a board. So this is a period where people develop peripheral chips and try to reduce the glue logic and try to eliminate multiple power supplies and multiple clock inputs. And this is well exemplified by the 8086, which in 78 come fully equipped with 5 peripheral DMA, interrupt, PIO, and so on, serial I/O. Then we get into the next period where basically IBM is breathing back on Intel's neck, since they own 10% or 20% of the company, and make sure probably that the 386 is a reasonably designed product, because as you may know, the 286 was not a reasonably designed product. And basically it's the lesson of the PC. We are now shipping in significant quantities products that are essentially personal data processing computers running applications that are very similar to mainframe applications, so we better be like what we have learned from mainframe. And then this era terminates with the 486, which in 1989 has a cache on board. By the way, the Z80,000 had a cache on board 3 years sooner, but in this case, like in all cases, you can only run history by talking about the dominant vendor. And so unfortunately, I have to talk about Intel a lot more time than I might wish. Another thing that was imported without any questioning, and has always puzzled me, was several concepts from mainframe that were never discussed. Now, some of them, it makes sense never to discuss them, But it is the case that they were imported without any question. The von Neumann architecture, in terms of binary coding, stored program memory, and the differentiation between logical or architectural design and implementation, was imported without any question. The customer focus, at first in the case of mainframe, it was table building, scientific and commercial, followed by I need to provide to my customer a complete system solution, and I need to provide software compatibility. This is the evolution of mainframe. You see this evolution happening with microprocessor in a much shrink fashion, and with never anybody obviously defending the fact that software compatibility is not a good idea. Although you can see that happening today when people talk about computer appliances and they try to help to explain to you that you don't need to have an x86 compatible architecture in one of those appliances because the software is not the same. I'm always been nervous about those kind of arguments. But the thing that was the most interesting import without questioning was the concept of software development cycle. A mainframe at first had been a case where people thought the hardware was so costly that software was free. And so they shipped software for free with the hardware. Quickly, IBM had hundreds of programmers developing software. So at some point, IBM decided to unbundle software, meaning to charge for software a different price than what they were charging from hardware. And then came the Mythical Man Month. The Mythical Man Month is, by the way, a very good book written by Mr. Brooks about his experience in writing the 360 operating system. And from that became the notion that software was like a tar pit. And people attempted to resolve that by structured programming in 1970. Remember, 1971 is the microprocessor. So all of those concepts were imported with microprocessor because basically, as you needed programmers, you hired people that had been trained as programmers. They'd been trained as programmers either in a university environment or in a mainframe environment, so you never questioned their education. Because you didn't question their education, then the reason to copy mainframe structure became even stronger. We're using the same kind of software, the same kind of knowledgeable people, then basically we're going to get the same kind of architectures. So what were the major hardware imports? At first it dealt with ALU and instruction set. But by 1974, most of the simple format of mainframe had been already copied. By 1979, with this 16-bit, essentially, there was no instruction invented in a mainframe environment that had not been copied or decided not to copy in a microprocessor environment. There's a very interesting thing related to the 286. The 286 copied the descriptor structure of the Honeywell machine in the Multics architecture, and to be honest, I have to say that was going overboard, and we've all suffered from that. The next issues were structures like floating point. The first computer to have hardware floating point was the 701 in 1954, and the next computer that had very significantly sophisticated floating point, like we would think of it today, was the Stretch in 61. This was copied by Intel in 1980 as an external chip, and then in 1989 as an internal chip. This is a place where there is a difference. Mainframe had a UNIVAC floating point, and an IBM floating point, and a DEC floating point. And if you know anything about numerical analysis, the difference in floating point format made that you got different answer if you run the same software in those different machines. So Von Kahn from Berkeley and Intel, having learned from the mistakes of a mainframe, designed a standard called the IEEE floating point, which attempted to resolve all those issues. And the IEEE floating point has become the dominant standard and is still now used in mainframe. So this is a difference that exists between the two. The first machine to invent prefetch was Stretch. Memory at that time was reaching the speed of 2 microseconds, and you had a CPU that required to fetch instruction at a slightly higher speed, that could execute instruction at slightly higher speed as a memory. So you overlap, in a pipelining sense, prefetch. The first microprocessor, 16-bit, implemented it. Then we got to microcode. Microcode was first commercially used in a sweeping fashion in mainframe in 65. where you had 6 different machines with very different price performance point, all implementing, thanks to microcode, different microcode in each machine, the same instruction set architecture. This was immediately used by the 8086 and the 68000 in 78 and 79. Maurice Wilk, we talked about him before, invented cache memory. He called it slave memory in 1965. This was used by the 360 Model 85. We talked about that. And the first time it was used in a microprocessor, to the best of my knowledge, is the Z8000. The R2000, the RISC architecture, used it externally, and Intel used it internally in 1989. Now, you know, when you are in 1985, there's no way you do not know that cache memory is going to get into a microprocessor one day. The question is when. It's not, there's no discovery, no invention in that sense. The thing that is the most interesting is in my mind pipelining. The very sophisticated, by the way, I urge you to buy, or to borrow from the library the issues of IBM Research and Development Journal, or whatever is the IBM Exact magazine, that cover the 360 Model 91, because you will discover that it is a stunning description of what we call advanced, you know, microprocessor pipelining concept, like instruction scheduling, branch prediction, and register renaming. All of those were invented in that time frame, and thus there is no invention that we have made in this. We have applied it to a different technology, but there's no invention there.
Bernard, that's republished, I believe, in large extent in Seward, Bell, and Newell.
Yes. Yes, we'll talk about that. Since I'm not doing too badly on time, I'll have a few minutes to talk about that. One of the issues that dominated mainframe was virtual memory. You know, when you didn't have virtual memory, you had to have a program that could fit in the memory in order to achieve its ability to execute. The minute you had virtual memory, you could start resolving some of the issues of memory allocation that were really quite a nightmare. And so it was invented in '62 in England by the Atlas I. By the way, what's fascinating about, there was an Atlas II machine. The Atlas II machine didn't have page virtual memory because they didn't really know if it was a good idea or not. And it was also followed by segmentation being invented, I believe, for the Bureau 5000 in 1960. The two were merged into Multics, which had both virtual memory that was segmented in page. And Multics was a project that started around '62, I believe, published significant amount of paper in '62 and '65, and influenced this Honeywell line of computer that run Multics, which then influenced the 286 to copy the descriptor architecture that was used in the Honeywell machine. And all of those culminated in a concept, now we're talking about mainframe concept, of capabilities. The first time-sharing system that had capability was the Carl time-sharing system, 1973. I thought capability was a bad idea, and I see that there are people talking again about capability today. But basically, this is a clear case where microprocessor, several years before the technology could afford you to have virtual memory, knew that it was coming. Now we get into the interesting part dealing with, is there a possibility that a changing application focus in microprocessor could result in a different type of path that has taken place in the past? Could we, in essence, see mainframe going in another direction and microprocessor going in another? Basically, my answer to that is no. And the answer to that is because we have not yet at a level of different application focus that could justify such a thing. In the past, we have done personal data processing, and personal data processing is no different from mainframe data processing to justify new architecture. The first thing that occurred was the emergence of a graphical user interface. Mainframe did not really have a need for graphical user interface, and graphical user interface are a very old idea. This will allow me to talk about a very important man in computer history called Mr. Licklider, who wrote a very famous paper in 1960 on mind-computer symbiosis, talking about the fact that you wanted to interface with a computer in a different fashion, and also, quite genuinely, telling you that the web will come one day. And he was very influential because he was the head of ARPA, which gave a lot of federal money to a lot of research projects. You have to realize that computer science in the US was developed through the help of federal money. It's only in 1965 that the amount of federal money in percentage for research dropped down from 90% to 50%, and then the industry was starting to rise above 50% of the research money. And ARPA was a defense group that basically gave enormous, at the time, amount of money to very few campuses to develop projects. The ARPANET is a result of that. Multics is a result of that. Time sharing is a result of that. Artificial intelligence may never have been a result of it. And now, what happened is he financed Doug Engelbart, and Doug did his demo. Doug is the inventor of the mouse, and Doug his demo in '68 that influenced a lot of people, resulting in the Alto being the first personal computer done at Xerox PARC that had a graphical user interface. And then Lisa and Macintosh copied it. It took many years for the PC environment to copy it for lack of resources and lack of standard. But by the time we reached 1990, Windows kernel environment is taking place. Very fascinating history. We copied it in personal computer. It didn't make a great change because graphical user interface does not really impact a microprocessor design. It might only impact on bitmap and some multiprocessing operation. So we get to, is there a type of application where we could see a change? Well, I don't think computing applications, computing appliances are the case, because it really would have an impact on software, but not really on the architecture of the microprocessor. I don't think virtual reality is it. It does require a lot of megaflops of, graphical operation, but that impacts the parallel coprocessor doing graphics. So maybe multimedia. Now that's interesting because this is a case where a new data type, meaning digital images, can be supported by a new set of instruction, MMX-like instruction, in a microprocessor. But is this a new architecture because we had a new data type and we added few new instructions to the instruction set of the architecture? And my answer is no. It is noticeable, it is important, but it is not a new architecture. So we basically left with the only potential divergence between mainframe and microprocessor that would be with the web, and at this point I could not predict that. I will finish in 2 slides. Basically, missing from microprocessor, still missing from microprocessor today. We do not have a single package having 2 microprocessors. This is not an unreasonable design. It's not perfect and it may not be needed, and since Windows 95 doesn't really support multiprocessing, we will have to wait a little longer. But the reality is mainframe did have multiprocessing very early. Honeywell was very famous for having multiple processing and multiple processor. There are some esoteric pipelining techniques that are not used, like multiple branch path execution. The greatest difference between mainframe and microprocessor, ideas not yet imported, is in the area of I/O. The mainframe dealt with the whole computer system. The microprocessor up until now was focused on the CPU only, so I/O architecture was pretty primitive, and we still look at a Pentium and look at its I/O architecture and say it's pretty primitive. But we can see that there is a reason why channel-like structure, USB is a channel-like structure, or FireWire is a channel-like structure, could be now imported and be part of a chunk of the microprocessor itself, and this farm I/O storage hierarchy could support some improvement. But again, it doesn't look like those are issues that would change architectural issues. So in conclusion, because the focus of microprocessor was data processing, personal data processing, microprocessors have copied in 25 years, what took 50 years to do for mainframe. There might be some differences in path in the future due to new things like the web, although I quite question it at this point. And I will spend 2 minutes talking about bibliography, because I think that's hot. You notice that I attempted to mention to you computers that everybody should know significant amount of information about, and this was the purpose of the talk, among other things. There are very few good books on computer history. This is clearly one of them, and it's the Campbell-Kelly Asprey. Its coverage of microprocessor is quite reasonable. There is no good book on the history of microprocessor, except for the nice chapters in this book. This is a very important book about the early history. Goldstein was one of the pioneers of ENIAC. And then there is two sequence of books that you should really know about. Any book that has Pugh, I think is pronounced his name. They are IBM early computer history. They are IBM 360 and 370, and they are IBM shaping the industry. Those three books in which Pugh is an author or co-author are very, very good books that talk about technology history, explain to you the issues and the concept, and are must read in my opinion. The other two series of books that I must read is the Bell and Newell and the Seviorek Bell and Newell, which are essentially reprints of articles on computer. And to me, I always thought this were just describing computer architecture, not the history of computer architecture. It was just architecture. And anybody should have those books in his library. And then there's a fairly interesting book about ENIAC to UNIVAC, which does explain the advantage that UNIVAC had at first in having better computer than IBM.
Bernard, give those to me. I'll put them up
Yes.
on the website.
Yes, I will. I'll mail it to you. This is it. Now I will take questions. I have some goodies I should show to you before I do that. Now, this is a shoe, and it has a computer in it. And I'm not going to exaggerate too much, but I think it's a 4004, so it's as much power as an ENIAC. And this is probably as much power as an ENIAC too. It's, when the microprocessor came out, people really felt quite genuinely that they could be used in education. So this was a tool for kids to learn about computation. There was difficulty wheels, and then you would do some arithmetic, and the computer would do it for you. I believe it also has an 4004 in it. So again, this is the power of an ENIAC, or close to it. Both of those are probably in the 72 to 74 time frame in terms of their dates. I also have something that probably is very hard for the camera to see, but I'm still going to try. This is a poster that was done by the museum and the Micro Design Resources, which is 25 years of computer history, and attempt to have, I don't remember how many, but like 200 chips on it. Chip photo for all those chips and where they were introduced. There are some chips that are not on this because we could not get the chip photo for those. A good example of it is the F8. Okay, and that I think is all. And how long do we have?
Well, we have about 10 minutes more.
Okay.
Lenny, were you going to say something about the Computer Museum?
I can say a couple words about the Computer Museum.
Okay.
Gwen, stand up. And this is Gwen Bell. Gwen Bell is the director of the Computer Museum in all places, I guess. I don't know what your official title is, Gwen.
My official title is founding president.
Founding
It
president.
sort of lets me do anything I want and not have any authority.
Okay. This is Len Shustek. Lenny is the director, I guess, of the Computer History
Chairman of
Project.
the Computer Museum History Center.
Okay, fine.
And I am a volunteer.
And, well, I'm a volunteer too. we do have a set before, though. I actually got into this business because about a year and a half ago I was teaching W282 in a building which I think doesn't exist anymore, actually, on Stanford's campus. And I was bringing in artifacts like this, like the 704 tube module, and realized that most of the students in the class had never seen a vacuum tube and didn't know what a punch card was. And transistors they sort of knew about. Core memory they thought was called core memory because it was the center of the machine. You know, it was the core of the machine, not because it had something to do with little things that had magnetic cores in them. I came away from that thinking that here we are in the middle of Silicon Valley. It's absolutely outrageous that there's no computer museum where people look at, celebrate, preserve the history of this computer technology that we devote our lives to all the time. So when I was finished with that course, I sort of went around the country looking at computer museums, resolved to start my own computer museum here because we obviously need one. And I ran into Gwen Bell and Gordon Bell in the Computer Museum in Boston, which has been there for about 15 years. started off within Digital Equipment Corporation, but then moved out, had an extravagant collection of computers, old computers to current computers, memorabilia, artifacts, photographs, films, videos, all of this stuff, most of which was in the back room in Boston, and you couldn't get to see it unless you knew Gwen and kind of asked her nicely to let you in the back room. Make a long story short, we had a lot of discussions. Gwen and Gordon Bell live out here now. We decided to move the collection that was in the back room in Boston out to here. It's all in a big warehouse at Moffett Field. We're going to start a museum. We don't have a public location yet, but we're fundraising and scouting out for locations to put the public museum. It's going to be focused on the history of computers and computer technology for adults, not for kids. We're concentrating now on building the collection and expanding it. As Bernard mentioned, we just got the Stretch computer, 1 of 7, from Livermore, plus a whole collection of other computers from Livermore, including a Star and a 7600 from CDC and a 6600 and a Cray 1 and a bunch of punch card machines and tube machines and all kinds of wonderful gadgets. Right now we're in collection phase. We've started a lecture series. We had a lecture about a week and a half ago by Gary Struckweather, who invented at Xerox PARC the first laser printer. And he gave us an interesting talk about the technology behind the laser printer and also the politics of getting a laser printer to be made in a company whose business was primarily copiers and not printers. He had to sort of fake it and make it seem to them like it was a long-distance copier, not a really. In any case, we're in business. If anybody wants to get involved, come to talk to any of us who are involved with the museum. About once a month, we have a Saturday work day where people can come down to the warehouse and help us unbox things, label things, clean things, sort things, figure out what we have and what we want to keep. What other activities do we have going on? We have this poster. We're, of course, in fundraising mode. We're a startup like all others, but venture capitalists are not going to fund us, or at least they don't know that yet, but they are. So we're looking for donors and people who want to become founding members of the Computer Museum, or people who just want to volunteer to help us. One of the things we're doing is setting up exhibits in public places since we don't have our own. We've done several at conferences and exhibitions. We're going to be doing one right here in the Gates building. We've got the faculty who have volunteered to pay out of their own pockets for having cases made on basement and floors, main floor and floors 2, 3, and 4 of this building. And sometime in the fall, we're going to be installing a whole series of exhibits that will rotate from quarter to quarter that have to do with the history of computers, the history of Stanford's involvement in computers, the Stanford Computer Science Department, the Stanford AI Lab, the companies that have been started by Stanford graduates, of which I'm sure you all know the litany of names. So that should be an exciting development until we eventually get to our own building. So that's the project. Thank you.
Thank you, Ken. Okay, any questions, comments?
Is there a website for the History Museum?
Yes, www.tcm.org.
Other questions?
No questions?
Yes.
What's kind of impressive, though, is not that the computers have changed so much. It's still a 360 program, but none of the I/O devices survive. The architecture, the instruction sets live much longer than the I/O devices.
Yes. I find this to be quite fascinating because if we look at the 360 architecture, which was a major understanding of the fact that there was 701 and 650s, and they were all different. I mean, IBM had 8 computers with 8 instruction sets just before the project 360 was started. And it was in response to the expenses associated with developing software for all of those. So they come with this architecture, which is one instruction architecture and one channel architecture, in essence. And then over the years, every 10 years, they change the channel architecture, meaning that basically the instruction set itself is not the dominant issue. So they start with wired-in channel architecture, and now they have essentially a channel architecture where basically which processor will handle the data from the channel and which device will handle it is totally dynamic. This kind of evolution doesn't seem to enter the minds of microprocessor designer today, and I find that to be amazing. I mean, I just can't believe we keep on talking about instruction set when the issue is I/O to me. But personal bias.
Bernard, do you have a whole bunch of 200 PPI tapes too?
Yeah, well, yes. Well, this
Anybody
is,
have a 200 VPI
yes,
tape
yes,
here?
yes. This is the comment also that has been made by others, is that if we think that electronic media is you know, timely and will be readable, you know, at all time, things about all those tapes I have at home that there's no device to read, and in which I thought I was storing important issues on.
Speaking of that, that was always my notion of the history museum, that you have at least one each of all these old peripherals, so you can read all our old data and convert it.
Having them is one thing, keeping them working is
No,
another.
you know, we need virtual versions of those.
Yes, I know. We need people to write simulator software so we can run all of those old peripherals and instruction set and be really being able to see what VisiCalc was all about, you know.
Well, it's kind of interesting that all the artifacts you brought were hardware. What about software artifacts? Are we collecting those?
We have Morris's worm, but should we let it out?
Well, you can put it in the cage and let it out and let it run there.
No, this brings an interesting issue which I think interests myself and Len and several other people quite significantly, which is how do we store and conserve software? I mean, if I give you a diskette, I didn't give you anything, but you want to see is the program running, and thus it goes back to the issue of how do you emulate all machine so we understand what was the level of software that people had. And apparently at this point, there is not, in my mind, enough taking place in that arena, because it's pretty complicated issue. And I certainly would want the museum to focus on software too. I mean, I do not mean to eliminate them.
Isn't the plan to somehow make that accessible through the web, I presume? And run your virtual old computers?
Oh, there are websites now, actually. There's one called the Museum of Retroactive Computing, and it's trying to collect together links to people who have emulators. That's one way to do it. There certainly are ways to present hardware artifacts on the web as well, and images and videos.
Tie them together.